when we look at Section 8.1, we're going to break it down into kind of 2 days. Today, there should be a lot of review, a lot of stuff that you've already seen before, maybe a couple tricks that you either didn't know last year or you did kind of talk about, but now we're going to review it a little bit more just to kind of refresh your memories with it. So today that's going to be what we focus on. Tomorrow we'll talk about some different types of ways to manipulate our functions to get them into a form that we do know how to integrate and so on. So we'll do a little bit more in depth tomorrow as well. So first thing, as far as integration goes, you need to know your basic rules. Okay, now when you talk about basic rules, we're talking about knowing how to integrate x to the n, or knowing how to integrate 1 over x, or knowing how to integrate any of those other things. Okay, so all your basic rules of integration. Integrating your trig function, sine, cosine, tangent, secant, cosecant, those sorts of things. So what I would recommend you guys do at some point, okay, look at page 508. Page 508 has a list. There's like 20 different integration rules that you need to make sure you absolutely know. Okay? Most of those 20 rules should be ones you already know from last year. They're ones that we talked about when we did those integration drill PowerPoint. All of those, they're included in that list there. Okay, so it's just a list of all different types of integration, just the basic integration techniques and what they come out to be. So what I would do is go through the ones that you're looking at, mark off the ones you know. So these are the ones I definitely remember. Mark off the ones, hey, I don't remember this one as much, because you have to memorize it. So if it's one you don't know or one you don't remember, it's one you definitely have to know. So to kind of highlight some, these are going to be very important integration rules that you need to make sure you memorize if you haven't already. Did you guys work with arcsine and arctangent a little bit last year?
Vaguely.
A little bit. Okay. So if you don't remember those, that's fine. That's why we're going through this stuff, is to review it all, make sure you kind of remember some of these little tricks and some of these different rules that you should know. So these 3 rules you need to make sure you have memorized. These are in that list on page 508. These are the last 3 you'll see at the bottom. Okay, so these are ones you definitely want to make sure you go back through, memorize what they look like. Okay, so the way these help is when you're looking at your integral, if you can get them into these different forms. So for arcsine, you need to have a value over the square root of a number. So a is going to be some number, and u is going to be your variable. Okay, so whatever expression has your variable included with it, that's going to be what we consider to be u, and then a is going to be some constant value. Okay, so when we have this set up, where we have our square root, we have an a squared, we have a u squared, we can have constants on top. All that constant on top does is move out front of our arcsine when we integrate, so those are just going to come along for the ride, just like normal. So we would take the arcsine of our variable, or the expression including our variable, over that constant value a, and then our integration constant plus c. Okay. Same thing with the arctangent function. The a value is just going to be some random constant, some number. U is going to be some expression with x, so this is going to be where our variable is. So when we integrate this sum of squares here, we have 1 over the constant value as arctangent of expression with x over a plus our integration constant. And then the last one is arcsecant. This is going to be a common one you might see. So this is one that looks almost identical to arcsine. The difference, though, is that the constant and x switch. So now we have our x value first squared minus our constant squared, and we have an extra value of our x variable outside the radical. So as far as integration goes, to use these three rules, you need to get it set up in a manner that matches these basic setups. So if we can get it to look like one of those forms, then all it is plugging into this rule formula and getting our values listed out that way. Okay with that? All right. So, one of the things that we need to make sure we do is recognize common patterns. So as far as using these integration techniques, being able to identify when we have certain patterns come up, there's a process we use every time. Okay? The other thing is we need to be able to tell the difference between when we use the different rules and not. So notice, if we look at these three integrals here, they all appear to be pretty much identical, right? What's the difference?
The x value in the numerator.
Yeah, so the bottom, the denominator stays the same all the way throughout. The only thing that's changing is we have a constant on top in the first value. We have a linear function on top in the second, so 4x, and then we have a quadratic function on top, 4x squared. So a factor of x is changing every time. And what happens is, even though they all look pretty much identical, they all get integrated differently. They all have different rules and patterns that apply. So if we take a look at that first one, what does that look like that we just got done discussing?
That looks like a...
Looks like the arctangent, right? Arctangent was dx over a squared plus u squared, right? So if I'm looking at this function here, or this integral, what would my u value be?
X.
Would be just x. Not the square, we want the square root, right? So u is just going to be our x. Our a value is going to be 5. Okay, so we have u squared and a squared. Now, since this is plus, does it matter what order they're in? No. So that's why for tangent, it doesn't matter. This time they put u first and a first. We can rewrite it. So a is first and u is second, just to keep things consistent. But with addition, it doesn't matter. Okay, so we can let u be x and a be 5. So the other thing then is we have this coefficient on top. So with our arctangent, it was just 1 dx over the u squared plus a squared, right? So when I go to integrate this, I can pull that constant out front. That's the same as any other time we integrate. Any constants can go out front, right? So now we're sitting here looking at our dx. Actually, since we're looking at terms of u, if I have u is equal to x, what's du?
Dx.
Dx. So if I have u here, du is equal to dx, so we can just replace that. So we've got du over our a squared, so 5 squared plus u squared, right? And when we have this format, with an a and a u, we can go directly into arctangent. So we have the 4 that comes along. And here's where just getting used to these arctangent, arcsine functions comes into play. So from the rule you wrote down, what would be the next part of my function here? So we have arctangent, but what comes before it? 1 over a, and we said a was 5, so we have 1 over 5. And then what goes in our arctangent function? U over a. So u is x, a is 5, so we go x over 5. And then we have our integration constant. Okay? And then if we wanted to, we could take it one step further and multiply the 4 by the 1/5. So you could be looking at 4/5 arctangent of x over 5 plus c. Okay? So if it's just a constant value in the numerator, and you have basically the sum of squares on the bottom, like x squared and another value squared, that's an arctangent. So as soon as you can get it set up into a manner of the u squared and a squared, arctangent, plug into the formula, you have your integration. Okay with that? Okay. Now, when we go to the next one, we can't use our tangent now because our tangent only works if we have a constant value in our numerator. But here we have a linear function in that numerator there. So if we look at this and we wanted to try to integrate this, what would be something we could probably try, or what could be something we could do here? Well, we could try to divide by x, but then we run into
The eternal
ours with
problem
the
of
constant
dx.
there. What was like your number one go-to move last year when you were trying to integrate?
UDU substitution.
U substitution, right? So is there something we could use in U substitution? Could we let U be something that would allow us to cancel out the other part of our integral here? What can we set as U?
X squared.
Yeah, the x squared plus 25 would be giving us the most fits, right, if we were going to try to integrate this. So let's let U equal x squared plus 25. When in doubt, take the most complicated part of the integral, let it be U, and see what happens. See what comes out when you do du, and see if it's something that we can work with to fish out whatever's left. So if I have U is equal to x squared plus 25, du would be equal to 2x dx, right? Well, this almost matches what I have left over. So if I were to replace this with u, I have 2x dx taken care of. What would I need to do with this to cover the rest?
Get rid of the extra 2.
We'd have to multiply by 2, right? So we need to multiply du by 2 to make this 4x dx, right? So basically that means I need to take my original integral and multiply by 2. So we need to have an extra factor of 2 in here. Now, when I use my u substitution, this just becomes 1 over u du. So want to see that? So 4x dx got taken care of with the 2 du. 1 over u for that x squared plus 25. So now we have something we know how to integrate. The integral of 1 over u becomes natural log. So the natural log of u plus our integration constant, which u now is x squared plus 25. So we get 2 times the natural log of x squared plus 25 plus c. I was able to get rid of the absolute values there. Yeah, x squared plus 25 is always going to be a positive value, so we don't have to worry about any negatives. Okay, if it's a function that would have to, or would have the possibility of negatives, we have to keep those absolute values on throughout to maintain the domain for natural log. Okay, so first example, we could use arctan. Second example, we'd use u substitution. What about for the third one here? And this is one you guys might not have dealt with. Did you guys talk about improper fractions or integrals at all last year?
Awesome.
Okay.
Doesn't even sound familiar.
So what you're looking at here now, if I try to use u substitution, so u substitution only works if I have one function with an exponent pretty much exactly one higher than the other function I'd be trying to get rid of, right? So if I think of these as two separate pieces here, this I can use as u because when I take the derivative, it's going to match my function above. But notice my exponents are exactly the same here, right? So if I tried to use u substitution, when I took the derivative, I'd have a value that would be too low exponentially. So I wouldn't be able to match up that derivative and get rid of the dx like I'd like to. So when you run across a problem like this, we call this an improper integral, which is going to be something else we talk about later on down the road too, but we have this improper integral. So what we're going to do is actually divide out these two expressions and then use that quotient to see if we can go ahead and integrate. So when we divide, We're going to need to use long division. You guys remember doing long division with functions back in pre-calc, I think it was?
We tend to avoid it if at all possible, I can tell you that much.
Okay, so long division. When you have an improper value like this, where the exponents are the same on top, you can't use U substitution. We run into this long division idea.
Definitely don't remember how to do it when larger expressions on the outside, I can say that much.
Okay, so when you do long division, the process is take the lead coefficient, so this x squared, and look how many times it goes into the lead coefficient on the inside. So what would I have to take x squared and multiply it by to get to 4x squared?
4.
4. And then make sure you match up values with their consistent spots. So in this case, notice I have put a 0x and 0. You want to put those in as placeholders. If you're missing any exponents along the line, you need to put a 0 placeholder in there to make sure you get things matched up correctly. So we have to multiply by 4. So if I take that 4 and multiply by x squared plus 25, so all we're doing is the original process of long division. It's just instead of numbers, now we have expressions. So 4 times x squared gives us 4x squared. 4 times 25 gives us
100.
plus 100. Notice again, match up like terms. So, when we get to this point, what would have been our next step in long division? Subtract. So we take 4x squared minus 4x squared, that gives us
0.
0. 0x minus 0 is
Here again, 0.
0. And then 0 minus 100 would be negative 100. Okay? Once we reach the point where the exponent outside is larger than the exponent inside, that's as far as we can go. So when we divide these two functions, we get a quotient of 4 with a remainder of negative 100. You remember how to write your remainders?
4 minus 100 over x plus 25.
Yeah, the minus 100 over the x plus 25, right? Or x squared plus 25. So what we're actually looking at here, if we take this expression and divide it out, it comes out to be 4 minus 100 over x squared plus 25.
Oh, hey, that's a bit more useful.
And now how does that help us? We can use arctangent on the 100 over x squared plus 25, and we can integrate 4 like we normally integrate 4, right? So if we integrate, 4 becomes 4x minus 100 times 1/5 arctangent x over 5, and then plus our integration constant. And so if we wanted to simplify a little bit, we could multiply the 100 in, so we'd get 4x minus 20 arctangent of x over 5 plus c. Okay with that? Okay. So as far as integration techniques go, these are just a couple that you can see. So you have just the or the right away arctangent. You have a U substitution type problem. This would probably still be one of your go-tos. It's just using U substitution to solve out. And then if it's one where the exponents are the same on top and bottom, there's no U substitution to do, you might look at long division and seeing what results, because it's usually going to come out to be something like this that we would be able to work with overall. Am I okay there? Okay. So let's try another one. So this one. So take a look at it, see what it looks like. Try to match it to something that you know from previous experience, or maybe one of the new ones.
So I said, oh.
Oh,
So-
yeah.
Yeah, that's what I said.
So this, I could have sworn. But the arc is like, that should be the.
Yeah, that's the one. No, I didn't. I don't know, I think it was chicken batteries or.
Okay, so what does this one kind of look like?
It's definitely one of the art things.
Okay, it looks a lot like ArcSine, right? Now, what's the issue with it right now as it stands? The x squared on top, right? So we want to see if we can go ahead and get rid of that x squared somehow by looking at what we have down here. Now notice, when we had this before, we have a u and an a we have to be able to define, right? So a in this case would be 5. U would be what? 2x to the third, okay? So when we're looking at this integral, what we're really looking at here is 5 squared minus 2x cubed squared. Everyone see that? So notice if we set u equal to our 2x cubed, what's going to happen when we take du?
U is 6x squared.
It's going to be 6x squared dx, right?
Oh, so we just need 1/6 now.
Yeah, so if we notice, this is going to take care of our x squared and dx, but we have an extra coefficient of 6, so we need to divide by 6, right? Because we want to get rid of the 6, we want only 1x squared dx in our value there. So we're going to take 1/6 times the integral. And now this 1/6 du replaces our x squared dx, so now we just have du over the square root of 5 squared minus u squared, right? Everyone okay with that step? And so, right here, we have our ArcSine set up exactly like we want it. So what are we going to have there?
1/6. ArcSine 2x cubed 5. Plus 6.
Everyone okay there? Okay. So there are times where you might notice or recognize an arcsine, an arctangent, arcsecant, something like that, but you might need to use u substitution within that to get to where you want to go. So in this case, we had to use u substitution with the 2x cubed to get rid of our x squared dx that we had in the way. And so then once we go ahead and get it into arcsine mode, we integrate, and then in this case, we just went ahead and plugged the x back in, which everyone's okay with, right? And there's our answer. Okay there? All right. Okay. So take a look at this one. So we'll look this one partway through. So what are we noticing right away here? We have x e to the x squared.
We've got a mismatch of powers.
Okay? So what do we have to do here? How would we go about integrating this or getting this to somewhere we can integrate?
We have to go to the not u, du, e to the u.
EU du? Or e to the u du? How would we do that?
You know, 1/2 on the outside.
Okay? So what would your u be? If we're going to use u substitution. So again, if you can, check u substitution right away, see if it's going to give us something that's useful. So what would I use as my u? X squared. If I let u equal x squared, what's du? Would be 2x dx, right? Well, so we have the x and dx. The only thing we don't want is the 2. So we would take our integral and multiply by 1/2. And now all I'm left with is e to the u du. And what's the integral of e to the u? E to the u. So I guess we'll just take it all the way here. There's our overall. So 1/2 e to the x squared plus c. Okay. Good there? So like I said, some of this might be pretty much review. We're just working on different integration techniques, recognizing different patterns. Going from there. Okay. So what are we thinking here?
You just need a 2 on the top and then you're good. I think. If you got 2 on the top, you could just do arc sine.
So it looks like it could possibly be arc sine, right? But what's the problem with that?
You get that x heavy.
Yeah, we have an x on top, right? We need a constant there. So we could try letting u equal x, right? So if we have u equal x and it work out, then we could still use our arc sine because du will take care of the x dx. But if I use u equal to x and I take the derivative, what's going to happen?
Just dx.
It's going to just be dx. So this is one where we can't use arc sine because we can't get rid of that linear aspect on the top at x. So what would be another thing we could do?
Division, I guess?
Yeah, we wouldn't necessarily want to do division, especially with a radical. The division would be it'd be a mess to try to get everything all situated. So first problem would probably be, let's try u substitution. So what's the biggest problem overall? What's the most complicated aspect of this equation, or this integral?
That denominator.
Yeah, the denominator. Okay, so let's go ahead and let u equal 4 minus x squared. So if u is equal to 4 minus x squared, what's du? Negative 2x dx. Well, there's my x dx, so all I need to do is get rid of the negative 2 by
Negative 1/2.
-1/2. So we'd have negative 1/2, the integral of 1 over square root of u du. And then this basically becomes a power rule. So you integrate from here, simplify, you transfer. Do we want to work this out the rest of the way, or are you guys okay from here? Good from here?
Do you mind working it out?
Working out?
Do you mind?
Sure. So if we're here, and I want to integrate this, so another way of thinking of 1 over square root of u is saying u to the negative 1/2, right?
Oh, okay, I get what you're saying here, I think I get it.
You're good then? Okay, so if we were to integrate that using the power rule, we'd have u to the positive 1/2 divided by 1/2, which basically means multiplied by 2. So you'd have negative u to the positive 1/2, u being 4 minus x squared, so you'd have negative square root of 4 minus x squared.
Thank you.
Okay. Let's do some trig. I know you guys love integrating with trig.
I am in pain just looking at this problem.
Okay, so if it's already in trig form, you can pretty much rule out arcsine, arctangent, arcsecant, right? So those aren't going to be an option. So instead, what would we probably want to try first?
Oh, no, U substitution?
Yeah, try u substitution. Okay. So now, what's the most complicated part of the integral here? The natural log. So the natural log of cosine of x, let's try letting that be u and see what happens here. So let's let u,
Wait, is the trig of that just tangent?
pretty close. So if we're going to let u equal natural log of cosine x, and we want to do the derivative, we basically just have a chain rule here. So if I want to take du, the derivative of natural log of anything is 1 over whatever's inside, right? So 1 over cosine x. But with the chain rule, then we have to multiply by the derivative of the inside, which is
Negative sine.
sine x or negative sine x?
Negative sine.
Negative sine x. Okay? So, when we take the derivative of natural log of cosine of x, oops, don't get our dx there, we get negative sine x over cosine x, which is
Negative tangent x.
negative tangent x. So du would be negative tangent x dx. So that takes care of my tangent x dx. The only thing I have to get rid of is the negative. So we have a negative integral of u du, right? So u takes care of the natural log of cosine x, du takes care of the tangent x dx. So if we integrate, we get negative
U squared over 2.
u squared over 2, which if we plug u back in, would be the negative natural log of cosine x squared over 2. Good there? Okay? Last one. Work with a partner, with yourself if you want to, try and figure that one out, see what you come up with.
Hey, you get that all the time. I would have Okay. Okay, what?
This one's really easy.
You see it. Oh, okay. I'm gonna go back so quickly.
Did you get on 1/5 arctangent to x/5?
Yep.
Okay, so it is easy.
He's so hot, and I was like.
That's not like you're trying to focus on it, so.
Move 1/2 out front.
She's got a
Well,
So I'm referencing something.
no, but you don't have to do that if there's no one. Do you?
Let's be you.
Oh, no, so you were right.
Awesome.
What do we think? Everybody get that?
I messed up a little.
We were lost.
Okay, so if you messed up, where did you probably mess up? The extra 1/2, okay? So on this one, when we look at u would be 2x, right? So if we take du, that would be equal to 2 dx, and we need our dx to be 1, right? So we'd have to take the 1/2 times the integral of du over the square root of r5 squared plus u squared. So in essence, when you guys are working with these, if it's not, if you're looking at that u, where the u is like a function like 2x here, you have to take your du and figure out what else you need to do with it to get it back to the constant you have on top initially. So you do need that extra 1/2 out front, so then when you have the 1/5 arctangent 2x over 5 plus c times a half gets you that 1/10. Good there? All right.
Fancy transition.
So there's your assignment.
I'm done with this. Sorry. So, what's like one is looking in here, so you never have any tables.
I'm not sure about that one. Is it a sketch?
Okay, then
All I need is
that's, I'm throwing the, okay, and. So that we do it, or then we, yeah.
Good, thanks. Okay, that looks longer than it really is. Just because it's so broken up, it's really not that long of an assignment. My answer key, I think, was the front page of one sheet and then like the top 2 lines or 3 lines of the second sheet. So
So not bad.
not too bad overall. I do write really small. But
Who called me 3 minutes ago? Who called me 3 minutes ago?